Now, the last part of Unit 1.2 is studying the existence of limits. So the first thing I want you to do is think to yourself, do limits always exist? Why do you think so? Yes or no? Why or why not? I want you to give me some complete sentences. Oh, maybe 2 to 3 sentences in your notebook as to why you believe limits always do or do not exist. Now, let's look at an example of what I mean. If I look at f of x is equal to the absolute value of x divided by x. Now, you know that this is the same thing as saying f of x is equal to, now the absolute value of x is just x when x is positive. So when x is positive, then the absolute value of x is just 1. When x is less than 0, the absolute value of x over x, this is going to be negative x. All right, and this is negative 1. And of course, it's not defined at x equals 0. So if I look at the limit as it goes to 0, we can see a couple of problems with this graph. First of all, I did this in the graphing calculator, and the graphing calculator, of course, was very, very happy to give me this weird kind of line. This is incorrect, so be very careful when you see nearly vertical or vertical lines on your graphing calculator. There may be something funky going on. If I'm looking at it when x is positive, the value is always positive 1. When I'm looking at it and x is negative, the value of the function is always negative 1. So we have this discontinuity. We have it not defined at 0. And we also have two different answers, whether we're coming in from the left or from the right. So this is one thing you need to be looking for to see if a limit exists. And clearly the limit as x goes to 0 doesn't exist in this case. Now let's look at this function. This is f of x is equal to x minus 2 divided by x squared minus x. I got confused there. Minus 2. All right. Now, that's not very good. That's okay. Let me erase it. I don't like things being messy. I really do have the eraser going. All right. Got carried away there. I have no idea what the lag time here is. Divided by. All right. Now, as we discussed before, at x equals negative 1, this function isn't even defined. Because this is what? X minus 2. All I'm doing is factoring the denominator. So when x is equal to negative 1, the function's undefined. Again, if you look on your graphing calculator, you're going to see this vertical kind of line. That's another indication that you have a limit that doesn't exist. You also see, as it gets very close to this x equals negative 1, the function kind of takes off. I mean, it looks like it stops right there. It really doesn't if you were to graph it correctly. Definitely not the way I just sketched it. The values take off. They become infinite the closer you get. So this is another situation where you're not going to have a limit existing. And this one's really cool. I like this one because it looks like there should be a limit, but there's not. f of x is cosine of 1 over x. Now look at this. It looks like you've got a really nice curve here. This is what my calculator did, or the online graphing calculator that I use. And you can see that it goes down and it starts oscillating. Now you see how this is almost flat there? That looks horizontal. That's because my calculator is stupid. My calculator doesn't know what it's doing. It doesn't know what to do in here because as you get arbitrarily close to 0, this number becomes infinite. Now, cosine of x is bounded by 1 and -1, always. All right. However, the function itself is going to sit in here and oscillate kind of wildly. And the closer you get to the origin, the more it oscillates. Now, we have just observed some common behaviors when you have a non-existent limit. Did you get the hint that the answer to your question was, should have been, no, limits don't always exist. By the way, that's always a trick question with math teachers. And the first one is f of x approaches a different number from the right side of c than it approaches from the left side. Anytime you have an absolute value function involved, chances are you're going to have this situation. Not always, but for the most part. If f increases or decreases without bound as x approaches c. Anytime you have a 1 over x situation, or 1 over x minus 1 type situation. Let's try 1 over x minus c. Whenever you have a 0 in the denominator, you're going to have this sort of behavior. And then, of course, when f of x oscillates between two fixed values as x approaches c. Oscillating is a key word here, folks. So you need to be looking for trig functions, sine or cosine of like 1 over x, something where it's going to be bound, and we'll discuss what that means later, but it's just going to squiggle between two fixed values, in this case for sine and cosine between 1 and -1. Oh goodness, went fast there. Now, turn up the tape and see if you can do these three problems. Now, we're going to go and look at the definition of a limit. Now, this is such a fantastic definition. I love this definition. When I took advanced calculus in grad school, I had just been a physics major. And in physics, we kind of took the bull by the horns and we just pretended like every function existed. We didn't care. We never proved existence. My husband was a mathematician and that made him crazy. And I didn't see why he wanted to bother with this sort of stuff. And the first test we took, this definition was on the test and it was worth 4 points. And tragically, someone in grad school made a 3 on that test. This is an essential definition and I want you to memorize it. I know. Memorize the definition. And I'm going to read through the definition and explain what it means. All right. Let f be a function defined on an open interval containing c. So f is just some function, and it doesn't matter what it does. And this is my xy axis. Whoops, that's not very good there. My pen's giving me some trouble, as usual. All right, vertical line here. Okay, now, on some open interval containing c. So if this is c right here, my open interval just has to contain it. All right, so c comes all the way down here. This is my open interval. All right, now it does not have to be defined at c. So f is defined on an open interval that contains c, but it doesn't have to be defined at c. And let L be the real number such that the limit as x approaches c of f of x is equal to L. So L is basically what the function appears to be approaching. Now, so the statement that the limit as x approaches c of f of x equals L means that for every epsilon greater than 0, there exists, and this is the important part, the existence of a delta greater than 0 such that if the absolute value of x minus c is less than delta, then the absolute value of f minus L is less than epsilon. Basically, what it means is if this L is equal to the limit of my function, and my function is f of x, here, it's always the curve. As I approach c, as I get in closer, then there is going to be a delta. And delta is just this distance right here, all right, from C, and we're approaching in the x direction, so that if I get x minus c, all right, minus c, to be less than this delta, then I'm going to force f of x to be close to L. And by close, I mean less than some epsilon. So this is L minus epsilon, and this is L plus epsilon. All right, I know this is a little confusing. Let me read through it as a sentence. The limit as x approaches c of f of x is equal to L means for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then f of x minus L is less than epsilon. Think about it. X approaches c forces f of x to approach L. That's all this means. That's kind of a fun definition to play with. Now, why in the world would you want to use this? There are some actual practical applications. Now, for this problem, it says a jeweler resizes a ring so its inner circumference is 6 centimeters. So remember, this is a circle. And I've lost my pen again. I hate this computer. Sorry, not your fault. All right, is it going to start drawing for me? Here's my circle. So the inner circumference is 6 centimeters. There it is. What's the radius of the ring? All right, let's just do the simple one first. You know the circumference is 2 pi r. So r is c divided by 2 pi. So if I look for the radius of the ring, then the radius is just going to be whatever my circumference is, and that's 6 centimeters. And I'm just going to leave this as 3 over pi. You can give me an exact answer of 0.9549 centimeters. On the homework, go on and take it out to 4, or you can round or truncate to 3. Now, if the ring's inner circumference can vary between 5.5 and 6.5, how does the radius vary? Okay, let's do B in a different color. So I'm going to go ahead. Okay, come on, pen. There it is. If R is C over 2 pi, here are my two choices. If it can be 5.5 centimeters, I'm going to put 5.5 in there, divided by 2 pi.